All right. In this video, actually, we'll talk about adjoint or adjugate of matrix A. That is about finding the inverse of a matrix using determinants. Okay. Anyway, if you just remember, when we talk about matrices, we actually studied how to find the inverse of the matrix by Gauss elimination methods. There's also one method, but here we're also going to learn another method using determinants. Okay, first let's talk about adjoint or adjugate, what we mean by this. And after that, you will see one example that's it about this video. All right, adjoint or adjugate of matrix A. Anyway, actually everything we are going to do here is we are going to develop a method to calculate or to find the inverse of a matrix A. If you're given, let's say, matrix A, whose size is n by n, we are talking about this matrix A. So we need to find its inverse. And we know that when we talk about the inverse, so for a matrix B, okay, let me just use blue or maybe lighter. For matrix A, for B to be its inverse, it must be actually equal to I. A times B equals I. Now here, A is given. So our task is we need to find B. So that's unknown. But instead of B, let me just write here, A times X is equal to I. The question is, we know that actually if this X satisfies this equation, then X is the inverse of A. A is given. How do we calculate this X? One way of actually finding this X is using Gauss elimination, right? We need to actually write here our super matrix here in this form, right? And we have to change this by applying a bunch of elementary operation into this form. Actually here, inverse. Let's say it's B, whatever we have here, that's actually inverse of matrix A. Okay. All right. Anyway, so now our question is this. Here, A times X is equal to I. Identity matrix A is given. The question is, how do you find this X? So now we will actually develop a technique to find this one. Now assume that, actually I just assume that the columns of X are numbered by this, that X1, X2, XC, X3, and Xn. Here, J is changing from 1 to M. And these are the columns of X. So here, actually, if you just write X here, we have something like this. X is like this, X1, X2, dot, 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 and here we have Xn. And each one is actually partitioned in this way. This X1 is the first column of X. If it's 2, it is 1, 2, 1, 3, 1, 1, 1, 2, 1, 3, blah, 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 right? Actually, here the rows are changing. 1, 1, 2, 1, 3, 1, 4, 1 plus n 1. If J equals 2, it gives us the second column of matrix A. If J equals 3, it gives us the third column. And this way, if J equals n, it gives us the last column of X. Okay. So actually, last time we talked about Cramer's rule. And by Cramer's rule, then what is actually one element of this vector here, Xij? And that is equal to this. I'm just applying Cramer's rule here. Why here? Because this Ax, if you just write here we have something like this, Ax. What is X? X is like this, the first column, and the second column, dot, 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 and here we have J's column, dot, 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 Xn. On the right-hand side, here we have I. And we know that each column of I is standard unit vector in n-dimensional space, E1, E2, dot, dot, and here we have En. So now if you bring this matrix inside, what do we have here? Here we have Ax1, Ax2, dot, dot, and here we have Axj, dot, dot, and here we have Axn. On the right-hand side, E1, dot, dot, here we have Ej, dot, dot, and here we have En, right? Columns. Actually, this column corresponds this column, right? Now, from here, that means that Axj must be equal to Ej. And from here, here xj, these are the components of xj. To find actually one solution, one component, right? I'm just applying the Cramer's rule. That is just Cramer's rule, just solving one equation here. Okay, so that is the solution of, this xj. Now the question is, what is it then? Because now we know that this xij, these are the components of this capital X, the matrix X. So now here, determinant of A, if A is given, we know how to compute determinant of A. So the question here is, how about this determinant of this Aij? And we know also what we mean by this. That means that I's column of matrix A is replaced by Ej, this unit vector, right? So if I just write this in matrix form, here this one, A1, 1, 2, 1, J1, N1, that's the first column of matrix A, and the second column. And how about, okay. And how about the J's column? Also here, let me just write here, J's column. So the first column, second column, blah, blah, blah. Here we have I's column. Okay, because here I's column is replaced by Ej. And what does Ej mean? Ej means J's component of this A is 1, and the rest of the components are 0. So that's here 0, 0, 0, 0. And here we have J's component. That's the first one, the second one, and third one, and this one J's one. So that's why in J's row, this one is actually in the J's row and in I's column, right? And if you just evaluate this, as you see here, if you just compute this determinant by cofactor expansion along the I's column, and the rest of the entries are 0 only, here we have 1. So here we have negative 1 to the power of j, because this is j's row, and i's column. Here we have j plus I. And here we have determinant of aji. And also we are familiar with this notation, right? Actually, what is it? It's just ji cofactor of this matrix. That is, what is it? Cji, right? Because minus 1 to the power j plus I, determinant of aji. Determinant of aji, what is it? It's just ji minor of this matrix. So now, here we have this cofactor of this A, or ji cofactor of A, is equal to this. So now if I just substitute that thing into this equation, we will get all the elements, or all the entries of X. So here we have Xij. Now instead of this determinant of Aij, instead of this, I can just substitute this one, Cji. So then what is A inverse? And here if I change from 1 to n, j change 1 to n, that gives us all the entries of matrix X. So here then A inverse, which is equal to X, that's equal to 1 over determinant of A times Cji. Cji, it's a matrix now. So 1 over determinant of A, just a number. And here we have Cji. If I just interchange the subsequent notations, here we will have Cij transpose, right? Because this one is transpose. So Cji, it actually deserves a special name, and we're going to call this adjoint of matrix A. What is Cji? That is Cij transpose. So that means that first just evaluate that thing, and after that transpose this, it gives us the adjoint of matrix A. And after that, if you just divide it by determinant of A, we will get the inverse of the matrix. That is how we obtain this formula. So the matrix Cji is called the adjoint or adjugate of A, and is denoted by ADG. That is adjoints, the first two letters of this word of A. So here we have just C11, C12, C1n, right? And C21, blah, 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 because that is transpose. Ij, but it's transpose. Okay, let's see one example. So that's actually the formula we have just proved. And now let's see one example for this. Use the adjoint method to compute the inverse of A. So also in the exam or quiz, if you are asked to actually evaluate or compute or find the inverse of the matrix using this method, you must use this method. If you just use other method like Gauss elimination method, you will not get any point. Okay, because also you need to be familiar with these methods. So what we have to do here, as you know, to calculate its inverse, first we have to find what is all the cofactors of matrix A, right? How many cofactors does it have? Since it has 9 entries, it has also 9 cofactors. Now starting from the first one, C11. So C11 is the first cofactor. So it is 1 plus 1 is positive. That's why the sign is plus. So we now have to get this. Just we need to delete the first row and the first column, right? And here we have 2, 4, and 3 minus 3. So here we have 2, 4, 3 minus 3. And we know how to compute 2 by 2 matrices determinant that's equal to negative 18, minus 6, minus 12 is equal to minus 18. And how about 2, 1? Actually, 2 plus 1 is 3. Negative 1 to the power is 3. That's negative 1. That's why here we have minus. And you just write one sign, and we don't have to each time mention this because plus, minus, the sign alternates here. So anyway, here's 2, 1. That means that we need to delete the second row and the first column. So here we have 2 minus 1, 3 minus 3. 2 minus 1, 3 minus 3. And evaluate this, we get 3. And how about C3, 1? 3, 1 cofactor of this matrix is, here it is plus 3, 1. We have to delete the third row and the first column, 2 minus 1, 2, 4. That's equal to 10. So in this way, I can calculate the others. C1, 2, we get 10. C2, 2, we get minus 2. C3, 2, we have minus 6. C1, 3, it is 4. And C2 is 3, that's negative 1. And C3, 3, that is negative 2. So what we have to do here is now we need to substitute, we need to find the adjoint of this matrix, right? And the adjoint of the matrix, actually, these are the entries of the adjoint of A. So now if you substitute here, that adjoint of A is, here we have C1, 1, 1, 2, 1, 3, but all of thing is transpose. First, let me substitute all the values, and after that, I will transpose this. And what is C1, 1? It is negative 18. C1, 2, it is 10. C1, 3, it is 4. We just found them in the previous video, minus 18, and 3, it is 10. So minus 18. It is 3, 10, and 10 minus 2, minus 6, 4, minus 1, minus 2. And if you just transpose this, right, it's just flipping about the, what is it, the main diagonal. 10 and 3, they interchange, and here we have 10, 3. 10, 4, here we have 4. 10 minus 6, negative 1, or minus 1, minus 6. So that is the adjoint of matrix A. So next step is now we need to calculate the determinant of A. And also actually we did a lot of examples about calculation. And here our matrix, right? And we know actually just applying some properties, we can calculate this very fast. If we just evaluate this, we get negative 2. So the determinant of matrix A is negative 2. So now using the formula, what is the inverse of A then? That's equal to 1 over determinant of A, that is 1 over negative 2, times adjoint of A. And adjoint of A, here we have found that. Just substitute here and simplify this, multiply each component by negative half, and we will get this matrix. So that is how we find the inverse of the matrix using adjoint methods. Okay. So we have another example. I can just show this by, I don't know, another video, or you can practice yourself. So that much is enough for about calculating these determinants. After having some break, I'm going to start 4.3. It is about eigenvalues and eigenvectors of n by n matrices. Now let's have break. After like 8 or 10 minutes, we will continue. Thank you.